today. That way you'll have a recording of it. I'll go ahead and make it available. I do need to update my videos. View as a single page. Okay, so this one's kind of long, so I don't know. I'm probably going to be tired after this one. So continuing this alternative chapter 8 on matrices and determinant, we have section 8.3 on matrix operations and their applications. Okay. So a few objectives here. We like to use matrix notation, understand what is meant by equal matrices, add and subtract matrices, perform scalar multiplication, solve matrix equations, multiply matrices, and model applied situations with matrix operations. Okay. So in the previous two sections, we looked at taking a linear system and using matrices to solve linear systems, and then also how to interpret different results that may pop up. So then now we're going to look at taking a system of equations and basically writing the whole thing as a matrix, right? And it's a little bit different, but we'll see. Let me show you what we mean. So an array of numbers arranged in rows and columns and placed in brackets is called a matrix. We can represent a matrix in two different ways. A capital letter such as A, B, or C can denote a matrix. A lowercase letter enclosed in brackets such as Aij can denote a matrix. Okay. A general element in a matrix A is denoted by Aij. This refers to the element in the ith row and jth column, right? So if we want to identify a specific location or specific element within a matrix, that's where we use those subscripts I and j. I is the row, j is the column. So a matrix of order m by n has m rows and n columns. If m is equal to n, then a matrix has the same number of rows as columns. It's called a square matrix. Okay. So given this matrix A, what's the order? So the m by n, the rows by the column, this is a 3 by 2 matrix. The entry in the first row, second column, so the order of this guy should be 3 by 2. The entry in row 1, column 2 is going to be -2, and row 3, column 1 is going to be a 1. So the order is 3 by 2. -2 and 1. Okay. Not too bad. So two matrices A and B are equal if and only if they have the same order n by n, and Aij equals Bij as I goes from 1 to m and j goes from 1 to n. Two matrices are equal if and only if they all have the same order and the corresponding elements are equal, right? So again, we're saying that two matrices are equal. They have to have the same size with the same corresponding entries. That's what this is saying. Okay. Let A be Aij and V be Bij, be matrices of order n by n. So to add two matrices, we basically add the corresponding components. To subtract two matrices, we subtract the corresponding components. Matrices of the same order, in other words, the same size, are added by adding the corresponding elements. So in order to add and subtract matrices, first they have to be the same size, then we add the corresponding entries. Okay. So perform this. Notice that if we go ahead and write out the order, this is rows by column. So this is 2 by 2. This is 2 by 2, right? So they have the same order or the same size. So we can add these together. Just add the corresponding entries. -4 plus 6 is a 2. Then 0. 7 plus 2 is a 9. And then it looks like that's a -10. All right, we just added the corresponding entries. So that's not too bad. Okay. I mean, I guess I could save it for Thursday. We'll have time on Thursday. So I'll finish this one out and then I'll save the other two sections for Thursday. That's fine. That way we can, because otherwise if I do it now, I'm still going to have to do it again on Thursday. So I'll just go ahead and do this now and then do that on Thursday just to be, Okay. Let's keep going. So we got 2, 0, 9, and -10. You see here 2, 0, 9, and -10. Okay, same thing here. Notice they have the same size. The order, so the rows by the column, this is 3 by 2, this is 3 by 2, so we can subtract them. We subtract the corresponding components. 5 minus -4 is 9. 4 minus 8 is -4. -3 minus 6 is -9. 7 minus 0 is a 7. 0 minus -5 is +5. 1 minus 3 is -2. Okay, so we had some double negatives going on there. You know, that takes a little bit of practice. That's okay. Let's just go style. That's decent. Oh no. 9, -4, -9, 7, 5, -2. 9, -4. Yeah, we got it. Okay. Oh no. Okay, let's back up. Okay, I think that's where we left off. Nice. Okay. So if A, B, and C are n by n matrices and 0 is the n by n 0 matrix, then the following properties are true. So matrix addition is commutative under addition. So we can say A plus B is the same as B plus A. We can reverse the order and we preserve equality. We have we can change the grouping. Matrix A plus matrix B plus C is going to be the same as A plus B plus C, right? So basically, in other words, we can regroup it and preserve equality. A plus the 0 matrix is equal to 0 plus the 0 matrix plus A, which is equal to A. So that's the additive identity. It exists. There's a matrix so that we can add it and preserve, you know, the original matrix. And then A plus negative A is going to be the same as negative A plus A. Those add up to 0. So that's an additive inverse, right? So we have an additive identity and we have additive inverses, okay? If matrix A is Aij is a matrix of order n by n, and C is a scalar is just like a real number, usually it's a non-zero real number, then the matrix CA is going to be the n by n matrix given by CA equals C times each entry. This matrix is obtained by multiplying each element of A by the real number C. So this is saying that C can be 0, but generally speaking, we don't multiply by 0 like that. But it can be 0. We call CA a scalar multiple of A. Okay. So if A is this and B is this, find -6 times B. Okay. So basically, we're just going to distribute a 6 into all the entries of element B. So then that's going to be a +6. That's going to be a +12, -48, -30. Okay. Okay. 6, 12. Come on. -48, -30. Go here. 6, 12. Yeah, we got it. Okay, let's keep going. If this is matrix A and matrix B, find 3A plus 2B, okay? So 3A is going to be what? -12, 3, 9, and 0, plus 2B, or not 2B. Okay, I couldn't resist, right? Poor dad joke. Uh-oh. Now so there are these guys on YouTube, they do these dead jokes. They be having me crack it up. Because they say it with a straight face, and they're clearly dead jokes, but they'd be funny. It's just these guys that sit around in chairs, like they'd be in different random places. I can't think of any jokes, so you know. Anywho, so 2B, that's going to be what? -2, -4, 16, and 10. And then if we add these two together, it's going to be a -14, -1, 25, and 10. Ooh, yep, I definitely am tired of talking for today. That is enough talking for one day. We're not too far off. It didn't take us that much longer, and it's only 12:15 now, right? We're actually going through this rather quickly. -14, -1, 25, and 10. You see it here. Okay. Okay, so properties of scalar multiplication. If A and B are n by n matrices and C and D are scalars, then the following properties are true. CD times A is going to be the same as C times D times A. So that's the associative property of scalar multiplication. One is basically a matrix where it's ones in all the entries. So 1 times A is A. Or actually, sorry, that's a scalar times a matrix. So that's just the number 1 distributed across A. It's just A. A scalar times A plus B, you can essentially distribute that scalar and get CA plus CB. And then the scalar C plus D times the matrix A, you can kind of left distribute like this and preserve it there, right? Notice that there's not I can't think of what I'm trying to say. I'm going to let it be for now. We're just going to go with this. So solve for x in the matrix equation 3x plus a equals b. Okay. 3x. Now, there's a couple of ways we can go about this. We could subtract. That would be okay. And we can multiply both sides by a third, right? So I'm going to solve for the matrix X before I do it, right? I'm going to do some matrix operation. Well, not matrix operations, but, you know. So, for instance, if we have 3x plus a equals b, we should be able to, I'm thinking subtract a on both sides, right? I think that's okay. So then we'll say 3x equals b minus a. I think that's okay. And then if we multiply both sides by a third, then x is going to be 1/3 times b minus a. I think this is okay. Okay, so let's do this. So then our matrix X is going to be 1/3 times B is going to be what? -10, 1, -9, and 17 minus A, 2, -8. Let's clean that up a little bit. 2, -8, 0, and 4. We're going to distribute a negative there. Okay. I'm going to keep this 1/3 for now. If I say B minus A, 10 minus -2 is a -12. 9, -9. 17 minus 4 is what? 13. Okay. And if we distribute a third, we get what? -4, 3, -3. Oh, is that 13? It's the only one that's a little weird. Well, we get 13 over 3. Style. Okay, so this is what we got when we did it. -4, 3, -3, and then 13 over 3. You see it here. -4, 3, -3, and 13 over 3. Okay. So I think they did the same thing that we did. We were given 3x plus a equals b. Subtract a on both sides, so we get 3x equals b minus a. And we don't really divide by 3, but we multiply both sides by a third, right? So if we multiply both sides by a third, we got the same thing. Then we plugged in our matrices and then did the arithmetic, and we got the same result. Okay. So now we've seen adding and subtracting matrices. So now we want to look at multiplying matrices. So if we say the matrix A times the matrix B, we always say the row times the column. So the first row of matrix A times the first column of matrix B. So AE plus BG, AE plus BG, right? We always do the row times the column, row times the column, row times the column, and then the row times the column, okay? So find AB given this A and this B, okay? So then AB is going to be, so we have this 1, 3, 2, 5. We want to multiply that by 4, 6, 1, and 0. Now, in order to do matrix multiplication, the number of columns of the first matrix has to match the number of rows of the second, right? So this just happens to be a 2 by 2 times a 2 by 2. And these guys already match, so we're in the clear, right? So then we always do the row times the column. So let me highlight it like this. We're going to say this row we don't need all of that. Let's fill it. So we're going to say this row, let me copy and paste. Now, how did you get over there? You guys are just jumping wherever you want to go. Paste. Hey, Google, give me a random color.
Orange. Orange is a bright color with a red hue. Traffic cone.
Yeah, you're not. Go ahead.
Just like the warm colors associated.
Oh my gosh, she's still talking. Is there a question? Yeah, you guys, you're not obligated to stay. Like, we're past the 15-minute mark or whatever. I'm just doing this for the sake of recording so you can use this. Because on Thursday, we're going to start with 8.4. So I'm just going ahead and do the recording now for this section. We're almost done. Oh no. But yeah, we're almost done. But again, you don't have to stay, but I'm just making the recording available so you can watch it at your leisure. I'm just doing it now. Okay. So now when we go to calculate this, we always do the row times the column, right? So let me see. The row times the column. So we're going to say what? 1 times 4. Let me clean it up. 1 times 4 plus 3 times 1. 3 times 1, right? That's the first entry. The next entry, we're going to do the row times the column. So that was going to be 1 times 6 plus 3 times 0. 3 times 0. Okay. So now we kind of reset. So this one, come on, goes here. This one goes here. Now we say row 2 times column 1. So we say the row times the column. So it's going to be 2 times 4. So that's 2 times 4 plus 5 times 1. 5 times 1. And then the last one, row times the column, 2 times 6. 2 times 6 plus 5 times 0. 5 times 0. Okay. All right, let's crunch these numbers. So that's going to be 4 plus 3 is a 7. 6. 6 plus 5 is 11. And that's 12. So that means A times B should be this guy here. Okay, that's how we multiply matrices. Okay. Okay. I actually feel okay. I'm kind of losing my voice a little bit. We have just a little over 10 slides remaining. I'm just going to finish this out and then I'll probably stop. Okay, we got 7, 6, 11, and 12. 7, 6, let's back up. 6 plus 5. Oh, that's a 4. Let me see. For that one, it should be 2 times 4. What? 13. 6 plus 5 is 11. That's definitely not right. Yeah. 8. Oh, 8. Oh, okay. 2 times 4. Duh. Okay, I got it. It's not a 6. I was doing 2 plus 4. Okay. So that's correct. 8 plus 5 is 13. Yeah. So undo whole. This is supposed to be 13. Okay, that's fine. Okay. That's another reason I'm stopping, because I know I'm kind of like, I am fading a bit. So the definition of matrix multiplication: the product of an n by n matrix A and an n by p matrix B is ultimately going to be an n by p matrix AB, whose elements are found as following. Basically, we just say the row times the column like we did. For the product of two matrices to be defined, the number of columns of the first matrix must equal the number of rows of the second. So that's where you see where I multiplied the green circles here. That's why I did that, because the number of columns of the first matrix has to match the number of rows of the second matrix. Okay. So if possible, so first we need to identify the order of each matrix. This is a 2 by 2 row times the column. So this is 2 rows times 3 columns. So notice that the number of columns matches the number of rows, so we're in the clear. So we can actually multiply these, okay? Okay, so let me get a copy of this guy. Let's see, I want this and I want this. Let's copy and paste this one. So we always do the row times the column. I'm going to say this row times each column. Okay. Okay. So then it's going to be 1 times 2 plus 3 times 0. I think I'm going to just write the answer in the interest of time. So that's going to be 2. Then the next one is 3 plus 15. So that's 18. Then the next one is -1 plus 12. Looks like it's 11. This one, 6 plus 3 is 9. So then we reset. Okay. So because of that 0, that should simplify a lot of the calculations. The first one is just going to be 0. That's going to be 0 plus 10, which is 10. That's going to be 0 plus 8, which is 8. And that's going to be 0 plus 2, which is 2. Okay, I feel like this is good. So I didn't write out the color coded. I didn't write out all the steps with this, and I just put the answers. If I need to show that, just let me know and I will. But I think you can keep up with it. 2, 18, 11, 9, 10, 8, 2. 2, 18, 11, 9, 10, 8, 2. Okay? Okay, now we officially have 10 slides remaining. Okay, so again, in order to do matrix multiplication, the number of columns of the first matrix has to match the number of rows, right? So rows by columns, this is a 2 by 4. This is a 2 by 2. No, that's not a 2. 2 by 2. So notice these two do not match. Bam, right? So we can't multiply these. So I'll just say we can't multiply. The number of columns in the first matrix does not equal the number of rows of the second, so therefore the product is undefined. Okay, so properties of matrix multiplication. If A, B, and C are matrices and C is a scalar, then the following properties are true. Assume that the order of each matrix is such that all operations in these properties are defined. So if we say matrix A times B and the net result times C, we can basically regroup them. So that's the associative property of matrix multiplication. If we have matrix A times B plus C, essentially we can distribute. This is distributive properties of matrix multiplication. And then say we had the matrix on the back-hand side, then we can left distribute, right? And then a scalar times a product, we can regroup the association, associative property of a scalar multiplication. Okay, we're almost done. Consider the triangle represented by this matrix, right? So we have our x coordinate and our y coordinates, right? So we have the origin, we have 3, 5, and 4, 2. Use matrix operations to move the triangle 3 units to the left and 1 unit down. So when we're going left, we're affecting our x value. So we're basically subtracting 3 from every x. And then to go 1 down, we're subtracting 1 from every y. I'm thinking I'm gonna just use my prepared notes. But if we subtract 3, right, from every x, I'll just put it here. It should be -3, 0, and 1. If we subtract 1 from every y, that's going to be -1, 4, and 1. So then that we will plot those points. 301, 141, 301, 141. Okay. Use matrix operations to, let me see how they wrote theirs. Okay, right? So we just did it, but here's how they captured it. So that way, when we're adding, we subtracted 3 from every x, we subtracted 1 from every y. Use matrix operations to enlarge a triangle to twice its original perimeter. I think we just want to multiply by 2, everything by 2. See? So everything by 2, we're just distributing a 2, and we get this result. It's not too bad. Okay. Find b times a. What effect does this have on the original triangle? So, let's see. Notice that b is what, a 2 by 2. A is a 2 by 3. So because this 2 matches this one, we can do b times a. Let me see if I can just write the result. So then b times a, if we say the row times the column, the first entry is going to be 0. Row times the column, that's going to be 3. Row times the column, and that's going to be 4. Then the second row, if we say row times the column, that's a 0. Row times the column, that's going to be a -5. Row times the column is going to be -2. Okay. So then we will plot these ordered pairs. Let's plot it. So we still have the origin. 3, -5 is here. 4, -2 is here. So it flipped it vertically. That's interesting. That was fun. As you can see, I don't get out much, right? Multiplying by b reflects the original triangle over the x-axis. That's interesting. Okay. We did it. It only took us 15 additional minutes, right? That wasn't too terribly bad. So we did make it through section, this alternate section 8.3. So what that means is that on Thursday, we will do 8.4 and 8.5. I'll go ahead and do my best to try to update my playlist on YouTube. I have all the recordings. I just need to basically just post them. So I'll do the best that I can to do that. Are there any, I don't know if we still have people hanging out. Are there any burning questions before we go our separate ways? Going once, going twice, forever hold your peas and rice. Okay. Let me go ahead and make a copy of this available in the box. That folder should be proper. When this bar finishes loading, you'll receive a copy of anything that you saw me writing. And so again, this will serve as our official recording for this. I went on and did it so that way now it's available. And then on Thursday, we'll start with this alternate 8.4 and 8.5, and then we'll finish up this, and then we'll kind of resume our regular schedule next week, okay? Okay, with that, we'll end the session here, and from one beautiful mind to another, enjoy the rest of your day, ladies and gentlemen. Take care. Peace.
Have a good one.
Just one.